All right, so yesterday what we looked at was applying this formula, which we learned actually the day before. The day before yesterday, we learned how to calculate the magnetic force acting on a charge that's moving in a magnetic field. Yesterday, what we did was we extended this idea to the following, to the fact that when you have a charge, if the charge is moving perpendicular to the magnetic field initially, then because the right-hand rule predicts accurately, I might add, that the direction of the force is always perpendicular to the direction of the motion, so it's force this way, and if it's moving this way and it's positive, that since those two things are perpendicular to each other, that force, although it's a net force and results in an acceleration, that force is not capable of speeding up the object or slowing down the object. And that's a very special type of acceleration called centripetal acceleration. The analysis goes like the following. The magnetic force is the net force. And again, I know you might get tired of hearing this, but it's not that there's two different forces that happen to be equal. There's one force, and we can call it the magnetic force, or we can call it the net force. The formula for magnetic force is you take Q times V times B. The formula for net force is you take mass times acceleration. So you're calculating the force in two different ways. It can be calculated using QVB, or it can be calculated using M times A. The acceleration is a special acceleration, which is centripetal, and centripetal acceleration is V squared over R, so you end up with this relationship at the bottom. And what you choose to do with that relationship depends on the question and is up to you. If you want to immediately fly into, which I do, QBR equals MV, I would do that. You're canceling one of the V's and then you're cross multiplying. The nice thing about that is everything is in a numerator. There's no fractions. So if you want to find any of these, you just divide by whatever's in the way. And that essentially was what we learned yesterday. So can you do me a favor, please? Take a look over your work and see if you're going to have any questions. I'll be right with you. Does anybody have any questions you would like me to go over? Go ahead, Zebby. 6? So we have a cathode. It's a CRT. It doesn't matter what that stands for. You know, I could make up some word, but it stands for a cathode ray tube. Electrons are accelerated from rest through a potential difference. They enter a magnetic field of a certain strength, and the question is, what's the radius? And this is a 1-2 punch physics principle question. On the one hand, so this goes back, everybody, to something I've told you before, that the philosophy of Alberta learning, and I agree with it, is students in Physics 30 who are the most successful are the ones who see the bigger picture. They're not necessarily the ones who memorize a formula, like QBR equals MB. Okay? They see the bigger picture. And the bigger picture here, there's actually two pictures we can look at. One is that you have electrons being accelerated. Doesn't matter how they get in there. I guess there's got to be a little hole for them to enter. They are accelerated through a potential difference. Okay. And then what's going to happen is, I need another little hole here. Then what's going to happen is the electrons will pass through this opening and they're going to hit a magnetic field. It doesn't really matter what the direction of the magnetic field is. I'm going to choose into the plane of the paper. So you got a lot going on here. On the one hand, over here you have a charge accelerated by a potential difference. And on the other hand, over here, you have a charge experiencing a perpendicular force. It happens to be a magnetic force, so I can put Fm there. Okay? And we have formulas to describe what's going on over here, and we also have formulas to describe what's going on over here. When we have a charged particle that is accelerated by a potential difference, what we can do is apply our formula for potential difference, which is potential difference equals change in energy over charge. And in a moment, that energy is going to become 1/2 mv squared in my written work. Really what it should be is 1/2 mv squared final minus 1/2 mv squared initial, but somewhere up here I'm assuming it says they're accelerated from rest, which means the initial kinetic energy, the initial kinetic energy is 0. On the other hand, this, and I'm going to go with your formula sheet here, is Fm, well actually I'm not, I guess, is Fm equals F net. What's going on in the second part of this diagram, in the right-hand part of my diagram for my explanation, is a lot more involved and complicated than what's going on here. What's going on the left is potential difference equals delta E over Q. So Q times potential difference equals 1/2 mv squared. So this formula is not on your formula sheet. But to go from a formula that is on your formula sheet to what we're going to use is, it's not a big deal. Right? Cross multiply, you put in 1/2 mv squared. What we're going to have to use here needs to be derived from this idea. And I already did that, but I'm going to do it again. Fm can be calculated using QVB. F net is always the mass times the acceleration, but it's a special type of acceleration in this question. And the reason why it's centripetal is because it's perpendicular. If the force is perpendicular to the direction of motion, it's centripetal motion, centripetal force, centripetal acceleration. We can replace in this formula the acceleration with v squared over r, because that's how centripetal acceleration is calculated. And don't worry about where that comes from. When I teach Physics 20, I don't even really explain where it comes from. It's a complicated thing. So I now have, that's a half. I don't know what it looks like, a 2, but that's a half. We now have two tools that we can use to describe the relationship between everything that's going on here. That's the bigger picture. Now you want to be careful not to necessarily jump into the bigger picture, because sometimes you don't need to. But in this case, what are we asked for? We're asked for the radius. When we look at the formula we derived, which I'm going to clean up by going QBR equals MV, and are you okay with that, Zebi? When you look at this formula that I've derived, to find the radius, we need to know the charge. Well, it's an electron, so we are aware of the charge. We need to know the magnetic field strength, but I believe we're told, yep, it's 2.2 times 10 to the negative 2 Tesla. We need to know the mass of the particle that is accelerating. Well, it's an electron, so we have that information. And we need to know the speed, but we don't know the speed. So that leads us to the reason why there's a second big picture here. Not only is there a big picture of centripetal motion, there's a big picture of this formula. So what you're going to do, and I'm assuming you know the voltage, right? Okay. What you're going to do is use this first to calculate V, to put V in here to calculate R. And I'm confident that you can do the calculations. Okay, so I'm not going to spend our time doing those calculations. But I want to talk about the physics principles. This is physics principle 2. When you, I better pull this up and show it to you on your formula sheet. I think it's 2. I better just double check. Yeah, it's two. It's what the Department of Education in Alberta calls uniform circular motion. It's accelerated motion, just like number one is accelerated motion. But number one is accelerated in a straight line or instantaneous acceleration. Um, number two is circular. So that's the physics principle there. That other formula, though, whenever you use it, and I don't know that this has come up yet, it's conservation of energy. That's what that formula is all about. There we go. This is physics principle 5, which is conservation of energy. The reason it's conservation of energy is that delta E equals Q delta V that we're making use of. I don't know if you remember, but I told you that in this formula here, when we first learned it, your delta E could be kinetic or potential, but not both. And the reason why this is conservation of energy is when you take the charge times the voltage, you're getting the potential energy available to give to the charge. And when we say, oh, we're going to make it equal to 1/2 mv squared, you're saying, well, the potential energy is converted to kinetic energy. So it's conservation of energy. As the potential energy decreases, the kinetic goes up. Is that okay? Does anybody have any other questions you would like me to go over? Yep. 7? So we have a particle. Now it's not an electron, so we need to be careful here. And I understand the reason why this question is being asked. Well, I don't quite know what it's asking. But imagine for a second here, I said to you, forget about this. What is Q? What if I said to you, what is the charge on the particle? Well, I could derive that whole thing again, but as much as I say, physics 30 students who are the most successful are the ones that see the bigger picture, sooner or later, no matter how successful you are, you accidentally memorize this, don't you? It's probably happened to most of you already. If you were writing some kind of an assignment, or next year in post-secondary you had a quiz or something, and you wrote QBR equals MV, I suspect that there'd be a big heavy X over it because you're not explaining where it's coming from. But are you okay with me starting there? Okay, so do we have enough information to calculate the charge? Well, the charge equals MV over over BR. I mean, this isn't wrong. I'm just saying it's a wrong place to start, okay, on a written problem. So let's do that calculation. We're going to take M times V which is 8.4 multiplied by 10 to the negative 27 multiplied by 5.6 times 10 to the 5. And I need to divide by the magnetic field, which is 0.28. And I also need to divide by the radius, of course, using standard units, so 0.035 meters. Want to make sure I've entered everything correctly before I go on. I think it looks okay. And you get this number, right? Now, it's a negatively charged particle. That's how many coulombs of negative charge it has. Now, why does an object become negatively charged? It becomes negatively charged because somehow or other extra electrons have been added to the object. And the charge of an electron the word is quantized. That's a word we're going to use later. The charge of an electron is a lump of charge. You cannot get a piece of it. You can't have part of the elementary charge. And if you take this charge on the calculator and you divide by the elementary charge, which is the charge on a single electron, you get 3. And what that means is that the only way the object can have a charge of negative 4.8 times 10 to the negative 19 coulombs is if we piled on 3 extra electrons. Now be careful because, maybe when you calculate the charge, you get that number. Well, maybe when you calculate the charge, you get that number on an exam. And you divide that by the elementary charge to find out how many of those lumps of elementary charge there are, and you get 3.0035. You're not going to say, oh, well, I did something wrong because it has to be exactly 3 or exactly 2 or exactly 4. In any science question, there's decimals involved and there's rounding involved, right? So you would assume it's 3. What I'm getting at here is the elementary charge is not exactly 1.6 times 10 to the negative 19. I think it's 1.602, something. Is that okay? All right, we're going to move on now. If you have further questions, we can always come back and look at them when we have more free time. So this is 30.2.10. This should say part 3 in your handout, right? This is actually part 3. The first part we looked at using the formula Fm equals QVB. The second part we looked at what that did to objects' paths, and it caused them to move in a circular orbit. And the third part is going to deal not with a single moving charge, but instead with the magnetic force on a wire. Okay? So the difference between yesterday and today is yesterday we were looking at the direction and the magnitude of the magnetic force on a single charge moving through a magnetic field. Like that beam of electrons that was moving from the back of this device to the front, when I held a magnet here, that beam of electrons was deflected. Each single charge was deflected. Here we're talking about an entire wire. Now, here's the reasoning, and this should make sense. I'll walk you through it. If a single charge, like an electron, when an electron is moving through a magnetic field, if that electron is forced, then if I have a whole wire carrying electrons moving through the wire, and the wire's in the magnetic field, the wire should be forced. And the reason is really simple. Each electron in the wire is experiencing a magnetic force. And if each electron in the wire is experiencing a magnetic force, and each electron is moving in the same direction, then the direction of the magnetic force on each electron will be the same. So the whole wire moves, is forced. And we're going to start off with a demonstration of that. We're not going to jump right into, I guess I'll talk about this first. The direction of the magnetic force is found using the same right-hand rule that we use to determine the direction of the magnetic force if it's a single charge. So I want you to just focus your attention. I don't have it. I know where I put it. I want you to focus your attention up here. This is the right-hand rule. Yeah. This is the right-hand rule, everybody, for a single moving charge. All right? So in this diagram that you're looking at, the magnetic field is north to south. So if I told you that a proton was moving in the direction of your thumb, you point your thumb in the direction of the motion of the particle, and the magnetic force is towards the floor, basically, out of the palm of your hand, right? And I want you to notice that I've got magnetic force on a moving charge, and this is the direction of motion of the charge, okay? Now watch what happens. Now I've got magnetic force on a wire carrying a current, and it's no longer motion of the charge, it's direction of the current. And we use I, don't worry about that letter. But I hope you can appreciate that the direction of the electric current is the direction of the motion of the charge. Because current is motion of charge. So there's not two right-hand rules. Your textbook talks about two different rules. It also uses left-hand rules, but there's one rule here for the motor effect. When you have a single charge experiencing a force because of its motion in a magnetic field, That's the motor effect. When you have a wire carrying a whole collection of charges moving in a magnetic field, that wire will be forced. That's the motor effect. So we're going to start off with a demonstration of this and predict the direction of the magnetic force. So what I have here, and I'll talk while I set it up, is I have a little kind of swing. So this thing can swing back and forth. And I'll let it settle down, and if it's not perfectly vertical because there's wires attached to it, I can adjust the balance on it. It looks like the bottom's got to go more this way a bit. That's pretty close. And what we have here, and I will highlight it for you on the screen just in case somebody ends up watching this on video, what we have is a bar that starts here. It's a metal aluminum bar. It's bent into a U shape. It goes here, and then it comes up the back. Then it comes up the back. And it goes behind a plastic block there. But the top of the U here is not connected to the top of the U that's behind there. It's just a U shape. Okay? But what we are going to do is we're going to connect the two sides of the U to a potential difference. If you look very carefully, and I'll fade this out so you can see it a little better, and I'll erase this because we don't need it. If you look very carefully, come on. There's a wire here, this red wire, that's connected right here to the U. You'll notice the wire looks a little bubbly, the insulation around it, and that's because we're going to run, well, I've already replaced the wires, we're going to run a fairly high current through here, and it melts and smokes sometimes, so the plastic melts. So that's going to be the positive, and I can see that I've wired it differently here, so what I'm going to do, no, I'll leave it. That's going to be the positive. The color of this wire is different than what I have up there, but we're going to ensure that this is the positive terminal, okay? So that's going to be positive on the front, and on the back of this, this will be negative. So basically, we're doing this. We're attaching a potential difference to that. And that means that, let's stick with conventional current. Conventional current will flow down here, and conventional current will flow in at the bottom. And the reason why I'm interested in that is that this part that's going in, where we're going to have conventional current going in, is between two magnets. So there's a magnetic field in here. And I want to just check to make sure that we have a north pole below and a south pole above. And I'm going to use my little thing, there it is. And we'll just check bottom. We want the bottom to be north, is that right? North, south, north. Bottom to be north? Is that what I have in there? Okay. And I want to set this up so that conventional current is going to be going in. So what I would like you to do is figure out, while I'm doing that, if conventional current is in, and the magnets are like this, which direction will this bottom part be forced when I run current through it? I want the front to be positive. The front is connected to the black. So don't be bothered by the fact that the colors are opposite here. I'll have to rewire it or change my diagram or something. So I just want to double check here. The positive terminal is connected to the front of this. Oh, no, we want the negative terminal connected to the front, don't we? according to this diagram. I've got a negative here. I think I might have switched from the previous picture, but let's do it this way. That will make more sense. The black is the negative. So I'm going to switch this. The negative is going to be on the front. There we go. So I'll double check. The negative says negative is connected to this wire, which goes to the front. So the front of this is negative. The positive is connected to the back. I'm going to turn this on. And I think I've got it set so that everything is dialed down. So you're seeing 2 zeros here. That means we have 0 voltage and 0 current. And you can see that the thing is pretty much hanging straight down. How many of you are confident you know which way it's going to be deflected or forced because of the right-hand rule? You're not sure. So the magnetic field is north to south. So imagine that this bottom magnet that you're looking at on the screen is the floor, and the top magnet is the ceiling. We have a north pole facing up and a south pole facing down. The magnetic field then in this space in between. So I've shrunk myself down and I'm walking around down here somewhere in this thing. The magnetic field is north to south. There's lots of ways I can hold my hand like that. What's the direction of conventional current? Well, conventional current is away from the negative. I know it says 0, but I don't trust it. Away from the negative, sorry, towards the negative. That's better. So it's this way. So which way should this be forced? Out of the palm of your hand, because we're thinking conventional current, it should be forced this way. I think the confusion arose because my previous picture, I had it the other way around, right? Okay, so we're going to go with this. And I think, just to let you know, I changed it to this because I wired it with the black wire on the front. Black is negative. Okay, but we can switch it around and see what will happen. So if I turn this on, there's no current right now. If I increase the dials to get a current, and this is a finicky kind of device. There's not just a current dial. There's 2 dials you got to work in tandem. But you can watch that, and I will increase this. There, we're at about 3.6 amps, and you can see the thing has been deflected to your left. And I'm going to dial this down just a bit. I'm going to go down to about 1.5 amps. You can still see it's deflected. And I'm going to turn it off. In anticipation, so the right-hand rule works for a wire. Okay. In anticipation of a question I'm going to ask in a bit, what do you think the amount of force on that conductor depends on? In fact, we can go to this part of your note package. It says, what 3 things do you think determine the amount of the magnetic force? So who can come up with one? And I guess what I'm asking is, I hope it's obvious that the angle that it's deflected at is a measurement in some way of how much it's forced. My question to you is, how can we get it to be deflected more or less? Sure, the amount of current. So right now we're at 1.5 amps. If I dial this down to, I'm not even watching at 0.9 amps, is it still deflected to your right, or sorry, to your left? Yes. Is it deflected as much? No. If I go, I was at 1.5 amps, I believe. If I really crank it to 5.3 amps, it's deflected even more. And, you know, it's even deflected more than what you're seeing. You're just seeing it being deflected that far because that's where the magnets kind of end. I can show you that there's a lot more force involved there if I take this and I move it over. Right? It's deflected quite a bit. But when I have it down here, it's kind of at the limits of the magnetic field. It's no longer in the magnetic field when it's way over there. So definitely the current. And we'll write these down in a second. What's something else I could do to change the amount? I want to go down a little bit. There we go. To change the amount that it's deflected, to change the amount of the magnetic force. Far ahead. Right, the strength of the magnets. Now, there's a couple of ways I can change the strength of the magnets. This is a little intuitive. It may not be obvious, but if I take those two magnets and I move them closer together, I will have a more intense magnetic field. And I can do that here. If I look at this, I know it's a big bar, but it's looking like it's about 5 degrees. Would you guys in this general area say it's about 5 degrees, according to that scale at the back? Like it's halfway between 0 and 10 is what I'm thinking. Yeah? Okay, so it's at 5 degrees, 1.5 amps. I'm going to turn this off just because I don't want to touch anything live here. Now it's gone. And I'm going to take these and move them further apart, which means I should have a weaker magnetic field if they're further apart. So I'll replace them back the way they were. Turn it on. We're still going to be, I hope, at 1 point. I'll change it to 1.5 amps. And when I look at this, it's hard to see, but how many of you, particularly the people here, can see it's less than 5 degrees now? Because you can actually see the 5 on the back, and you couldn't see that before. So the strength of the magnetic field makes a difference as well. I can easily increase the strength of the magnetic field. I'll go back to when they were close together. And this should be about 5 degrees. And what do we have? We have a south pole. We have the magnetic field up, right? So south pole needs to be on the bottom. So I am going to add another magnet to this in a way that increases the magnetic field strength up. Well, I'll just put it in there. Put it about the same position. It's got to find its equilibrium here between gravity and it's hard to see, but it's a little bit more than 5 degrees now. It's deflected more. This thing, by the way, is really kind of a mysterious thing when you look at it. I'm going to turn this around so we can get it deflected the other way. I'm going to turn the magnets this way. It's really kind of an interesting thing. It's kind of spooky, but you know, all this is a voltmeter. You guys have seen voltmeters with a needle on it? And when there's more current, you've never seen a voltmeter with a needle on it? How many of you have? Okay. Well, they're called analog meters. I mean, they're actually really very, very accurate compared to digital ones. Digital ones can be glitchy. And if you've ever worked with a digital multimeter, if the connection is not perfect, the numbers bounce all over the place. But you get an analog meter and that needle goes over and it's steady. And that's all that you'd find in That's all that you would find in a voltmeter or an ammeter, is you would find something set up like this. We should be doing a lab later in the next unit where you're going to have to use a voltmeter. So this is what a digital voltmeter looks like. It's got a little needle there, and when you apply a potential difference here, just like we're applying a potential difference here, the needle is deflected, and it tells you the voltage. It's calibrated to tell you the voltage. So rather than me saying there's angles there, I could say that this is 3.2 amps. I could put a little mark on that wood, and then I could change it to 2.2 amps, and I could put a little mark, and I could make a scale. So that's all that this thing is like a voltmeter or an ammeter. There's one more thing that can change the amount of magnetic force, and it's not something I can show you here. Does anybody have any ideas here? So we can increase the current. That will increase the force. We can make the magnetic field stronger. That will increase the force. There's one more thing. Evan? Can you repeat that, please? Ah, without using something other than electrons, that's good. If we could somehow get alpha particles going through, then each alpha particle will experience twice the force. Let's face it, everybody, the force that is moving this thing is, in fact, this force, right? It's just that every electron is being forced. And Evan's mind, I think, went to this, that, well, if we have more current, then you're getting more electrons flowing more rapidly. Magnetic field, that makes sense. And then he thought, well, let's just have a different charge. So I'm going to change the question and say, without reinventing the universe, we have to go with electrons in this wire. How can you get a different force? And it does have something to do with the charge. You know what the answer is? Just have more electrons in there. And how we do that is you get a thicker wire. Or instead of having the wire do this through the magnetic field, which is in here, you have the wire do this. And now all of a sudden you have 3 times as much wire in the magnetic field. And if you have 3 times as much wire, then you have 3 times as many electrons being forced, so you're going to have 3 times as much force. And what we basically say is, if we can increase the length of the wire in the magnetic field. So another way to do this is if you have these magnets, this is a different view of the same thing. And this is the part of the wire that's being forced. Okay, this is the thing that's hanging. And each electron in this region is being forced because that's where the magnetic field is. You know what you can do? Is have longer magnets. We're not changing the strength of the magnetic field in this diagram. What you're doing is you're just having a magnetic field that is in a bigger space. So you have twice as much wire in the magnetic field. That's equivalent to wrapping it around twice. So now getting back to this, the 3 things are the current in the wire. And traditionally what we do in order to get a greater current is you increase the voltage. I'm going to turn this off now. I think you get the idea. Well, let's crank it up. Let's go to 20 amps. It's quite a tremendous force because the greater the angle that I get this to be at, the more I'm working against gravity. Oh! That's okay. I'll replace those wires. Can you read what it says? Let me get rid of this. Can you read what it says there? 5 amps max. So there's a reason for that, right? The wire is only capable of handling 5 amps because all that electrical energy that those electrons are losing, if you have a greater current, then you have more electrons losing that energy, and that energy is dissipated as heat, produces heat. So the current in the wire. This is the third one that I can't really demonstrate here. I could, but I've lost something. This thing was purchased with 2 of these. So you'd put the one there and you'd have the wire in and it would be deflected like that. Then you would take a second one and you'd put them side by side and it would be deflected more. I just have to make something like that. and I haven't gotten around to it. And then the magnetic field. And it turns out nature is very kind to us here. If you multiply those three things together, you get the magnetic force, strangely enough. So the formula, let me get rid of this now so it's out of your way. The formula is really simple. It's the magnetic force equals I. I is the current. And then L is the length of wire in the field, and B, which is the magnetic field. We do have to talk a little bit about current. In physics 20 years ago, we used to teach current, electricity, voltage, resistance, current, all that. We don't anymore. So the formula I'm about to show you, which defines current, is only being taught to you basically so you can use it in this. This is your formula for current, and it's on your formula sheet. I is equal to Q over T. And if you look at what the Q and T are, we understand what those variables are. Q is charge in coulombs, T is time in seconds. So current is how quickly charge moves. If you have a current of 10 amps, the charge is really moving quickly. A lot of coulombs per second. A lot. In fact, if it's 10 amps, it's 10 coulombs per second. So rather than writing a coulomb per second, we can write an amp. And that leads us into the first question. What's the current in a wire if here's a cross section of the wire? If you have electrons passing through that cross section of the wire and you have 20 coulombs of charge moving in 4 seconds. Well, I don't even think you need a calculator for this. I mean, you can use a calculator because we're so used to it, but it's charge over time. Current equals charge divided by time. So that's 20 coulombs divided by 4 seconds, which is 5 coulombs per second, or 5 amps. I don't know if you remember. Remember me telling you the amount of current that can be fatal? 70 milliamps. I'm sure I had this conversation in this class. Does that ring a bell? 0.07 amps. Oh, I did when I set up this thing, and I told you, we're going to be looking at 5, 10, 15, 20, 25 amps. Less than 100, less than a tenth of an amp can be fatal, so help me out and make sure I don't touch anything live. Right? 5 amps is like, that's dangerous. Okay, so it's a huge current. By the way, the little smoking of the wire there, that's why we have circuit breakers in our electrical systems in our house, is if you happen to somehow get more current than the device should be able to handle safely, the circuit breaker opens, which means it takes the circuit in that house that you're on and it opens it up so no electrons flow. It's a safety thing. Number 2, we've got well, we're going to use this for 2, 3, 4, and 5. We've got a piece of conductive material. It's the big, thick, cylindrical piece of wire. It has 6.5 centimeters length. Now, I want to be careful here and make sure that you understand 6.5 centimeter length lies perpendicular to the magnetic field. What that means, everybody, is that distance is 6.5 centimeters. It's the length of the wire that's in the magnetic field. The whole wire itself could be a mile long. It's only the part of the wire that's in the magnetic field that we care about. We've got a mass of this wire, and the magnetic field is 82 millitesla. What's the first question? Which is actually number 2, right? Okay. If the current is 2.8 amps, what's the magnetic force? Oh, that's pretty easy. Fm equals ILB. So we're going to take the 2.8 amps, multiply by the distance, and then multiply by the magnetic field. Did I see 82 millitesla? Was that right? It is, okay. So that's 0.082 Tesla. That's it. There's not much to this lesson in terms of thought for calculations. 2.8 times 0.065 times 0.082. Come on, you guys, help me out here. Help a fellow out. Okay, let's try that again. 2.8 times 0.065 times 0.082. Just want to double check. 6.5 centimeters, 82 millitesla. I get 1.5 times 10 to the negative 2 newtons. No? Okay, good. So about 1.5 times 10 to the negative 2 newtons. No, just a second here. It said find the magnetic force, but force is a vector, so maybe we should put a direction on that. What's the direction of the magnetic force? And I realize that we skipped over the couple of questions on the previous page, but I think we're okay. At the very top, we were asked to find directions. Let's just do it here. So, fingers of your right hand, I'm not going to demonstrate this. I'm just going to verbally tell you what you should be doing. You need to point the fingers of your right hand in the direction of the magnetic field, and you need to point the thumb of your right hand in the direction of conventional current, if that's what you want to do, or in the direction of electron flow, if that's what you want to do. And if you point your thumb in the direction of conventional current, then you're going to be looking at the palm of your hand. If you point your thumb in the direction of electron flow, you're going to look at the back of your hand. And we should get a magnetic force up towards the top of the page. Magnetic field this way. How many of you chose conventional current? So for those people, your thumb comes out and the palm of your hand is facing the top of the page. How many of you chose electrons? I guess pretty much everybody else. Your thumb would go in, away from the negative, and that would mean you look at the back of your hand, so it's towards the top of the page. So let's add that to our answer. I'm just going to say up, which is maybe a little lazy. We should probably write towards the top of the page, but up is good enough. I hope you understand when I say up, I don't mean up like away from the surface of the earth. So once again, magnetic field in this region is north to south. That's the direction our fingers have to point. If you use conventional current is this way, because conventional current is, that's a C, is towards the negative, because conventional current is positive. So you end up with your hand in this situation, which means the palm of your hand is facing up. Okay. 3, if the current is 2.8 amps, find the net force. Well, didn't we just do that? Didn't we just find the net force? No, we found the magnetic force. There's another force acting on the wire. It's the force of gravity, which is down. We already know this is the end view of the wire. We already know there's a magnetic force up equal to, we said 1.5 times 10 to the negative 2 newtons. Calculate the gravitational force down. That's just mg, right? That's Fg equals mg. I believe it was 1.2 grams. What was the mass of the wire? 1.2, thank you. 1.2, that's times 10 to the negative 3 kilograms times 9.81 newtons per kilogram. Gives me 1.18 times 10 to the negative 2, which is a little bit less than the magnetic force's magnitude. Not much, but a little bit. I'm going to exaggerate this in my drawing. 1.177 times 10 to the negative 2 newtons. So the net force, here we are again, look, this is a physics 20 question. What's the net force? Well, you add the forces. How do you add them? Well, if they're in opposite directions, you subtract the magnitudes and slap a label on your answer that matches the bigger direction, bigger force. The only thing that's physics 30 about this is calculating that upward magnetic force. So the net force in this example will have a magnitude equal to 1.5 times 10 to the negative 2 newtons minus 1.177 times 10 to the negative 2 newtons. The direction, of course, will be up. Carrying all of my decimals, I get 3.2 times 10 to the negative 3 newtons. Up. We okay with that? Liam? Okay. What we are, nobody's ever asked that, and I'm glad you did. It didn't occur to me that what I think you're thinking a student would think, but I think I know what you're thinking. You're saying to yourself that towards the surface of the earth is through the piece of paper, right? I get that. But there's this kind of underlying assumption that when we look at a picture, we're looking at it as we would look at it standing up. So if I said to you, build this thing, you would put two magnets on the table up here which would have the same orientation. And it never really occurred to me, that's what you were thinking, right? It never really occurred to me that, yeah, when you're looking at a picture of something on paper, unless it's explicitly saying it's a map or the surface of the earth, you're assuming that what you're looking at looks like this. So to really drive it home, and I think this is an important point, if I give you a sheet of paper, and I realize this is a little bit different, but I draw a house on that sheet of paper. When I draw you a picture of a house, I draw it this way. I don't draw it upside down or sideways, right? Does that answer your question? Okay. That's a good question, though. All right, let's move on. Let's take a look at the next one. Number 3. We just did number 3. Number 4. What would the answer to question 3 above be if I switched the potential difference? If I switched the potential difference, not necessarily interested in an answer, but how would that change the situation if I switched the orientation of the potential difference? Right, so the electrons would be moving in the opposite direction. What would that change? The magnetic force would be in the opposite direction, which would mean the magnetic force would be down. So the only difference now is we still have those same two numbers. 1.177 times 10 to the negative 2 newtons is gravity, but the magnetic force of 1.5 times 10 to the negative 2 newtons would now be down. So we would add them, 1.4924 times 10 to the negative 2 plus, be careful here, when I say we would add them, we were adding the forces before as well. It's just that to add the forces, you subtracted the magnitudes. Here, we're literally adding the magnitudes. What else do we have? 1.177 times 10 to the negative 2. I think that's right. So you get about 2.7 times 10 to the negative 2 newtons. And the direction of that net force would be down. It's all about force analysis. So when we look at 5, 5 says what current would be required to suspend the wire? Well, if it's suspended, that means it's motionless. That means it's experiencing no acceleration. That means the net force is zero. And if the net force is zero, that means the forces are balanced. Just because something is stationary doesn't mean there's no forces acting on it. There could be a million forces acting on it, but they all balance. So the idea here is that if this is the cross section of the wire and this is the magnetic force, the force due to gravity is equal in magnitude but opposite in direction. In which case we can do this. ILB equals mg. So the current that would accomplish this magical levitation would be mg over lb. I'm going to go by memory here, so I may need some help, but I believe the mass was 1.2 grams. The length of the wire in the magnetic field was 6.5 centimeters, and the magnetic field was 82 millitesla. So the answer to this question is 2.2 amps. Which, kind of makes sense because at 2.8 amps, there was a greater force up. So we need less than 2.8. Is this question number 6? Okay, so in question 6, we have this diagram, and each of these wires has a circular magnetic field around it. So the fact of the matter is that each wire behaves like a magnet. So the two things will either pull together or repel, and the question is, which will they do? And this is a very, very complicated conceptual question. So I'm going to show you what will happen first in the hopes that if you ever have to say what happens, you will remember it. And then I'll tell you how I remember it. So what I have here is two wires. They're just lamp cord wires, and they're both connected on the bottom to a positive and on the top to a negative. So what I have up here leaning against the board is essentially this. Okay. I've just, to engineer it a little better, I've just taken these two wires at the bottom and twisted them together. That way I don't have to have multiple clips. And in order to get a really strong current, I'm using a car battery. So, who saved my life? Somebody just saved my life. Could have had a big scar on my forehead. Okay. Better be worth it after all this. Okay, so I'll connect it. They come together. Now, how many of you guessed they come together? It's a 50-50 shot, though, right? I mean, like, why do they come together? This is really complicated for me to explain. So first of all, I want you to remember that if the currents are in the same direction, the wires will be attracted. I remember this because of the demonstration I saw in university, and I've tried this, and the slinky just melts, okay? A prof had a slinky, a metal slinky, that was hanging, so it was stretched out. And he connected one terminal of the battery to the bottom and one to the top. And if you think about what happens then, around each curve of the slinky, the electrons will be traveling in the same direction. So they're traveling this way in one curve, and then they come around, and they still travel in that way. And what I remember visually is the slinky went, it got shorter. So you can remember that. And maybe tomorrow, because I do want to give you enough time to practice some of these problems today, I will show you what happens if they're in opposite directions, and it's no surprise they do this. The reason for that is the following. This is really tricky. Around this wire, there is a magnetic field that circles it. I would like you to wrap your mind and your right hand around that wire so that you get a visual of what the magnetic field would look like. And what it's going to look like, I'm going to draw this in a very judicious way, is it will look like this. Correct? Okay. So, this is the magnetic field associated with wire 2. This is wire 1. Now, that means wire 1 is in a magnetic field, isn't it? Just like the hanging wire was in the magnetic field. So we ought to be able to predict the direction of the force on wire 1 due to wire 2's magnetic field. Now the magnetic field of wire 2 right here is out. It goes around the front, into the board, behind to the left, and then out on the right. So what have we got going on here? Wire 1 is in a magnetic field that is out, and conventional current in wire 1 is towards the top of the page, which means the right-hand rule predicts that wire 1 will be forced that way. And then you can repeat the process and imagine wire 2 being in wire 1's magnetic field, which I'm just going to do in a different color. Wire 1's magnetic field looks like this. Well, kind of like that. And the magnetic field of wire 1 here is in. So as far as wire 2 is concerned, wire 2 is in a magnetic field that's in. Wire 2's electron flow is down, so conventional current is up. The right-hand rule predicts that wire 2 experiences a magnetic force, to the left. It's an interesting demo. It really is, I was going to use the word shocking, but I didn't want to make a dumb joke. It really is dramatic, isn't it? Like they're pulled together quite dramatically. So I show it to you because, I mean, you want to try to make the class interesting from time to time. And you might be asked this on an exam. The thing that's surprising is you think the currents are in the same direction, so similar things repel. But really, when you look at the two magnetic fields between the wires, the two magnetic fields are in opposite directions. One's going in, one's going out, so they pull together. Anyway, that's the lesson for today. You only have about 10 minutes, which is typical. I'll show this demo to you probably tomorrow. There are a lot of other ways to demonstrate this magnetic force on a wire. But from now on, everybody, when I talk about the formula on the left, I'm talking about the deflection of electrons, let's just say, which we looked at that demonstration. If you're watching the video, you don't know what I'm indicating, and that's okay. But the formula on the left is for the magnetic force on a single charge. The formula on the right is the magnetic force on a wire. Okay. So you have a few questions to do for tomorrow. We'll go over them tomorrow. I would like to do a couple more demonstrations with this. We are one lesson away from being done. So tomorrow we're going to be doing a lot of demonstrations with this final lesson that will start tomorrow, plus a couple more from this lesson. We may not finish the unit till Monday, but your exam is sticking on Thursday of next week.